To calculate single-family dwelling loads according to the 1987 National Electrical Code, firstly, you must determine the electrical characteristics. This includes noting the square footage of the dwelling, the number of occupants, and the occupancy type, which is typically a residence. Secondly, calculate the base load. This involves the lighting load, which is generally calculated at 3 watts per square foot, and the small appliance load, which is typically 1500 watts. Thirdly, calculate the heating and cooling load. For electric resistance heating, use 10 watts per square foot. For cooling load, use 3.3 watts per square foot. Fourthly, calculate miscellaneous loads. This includes water heating, often around 1200 watts, an electric range at 8 kilowatts, an electric dryer at 5.5 kilowatts, an electric oven at 2.4 kilowatts, and air conditioning at 1.25 kilowatts per ton of cooling. Also, consider other loads like dishwashers, garbage disposals, and ceiling fans, estimating their consumption from their appliance specifications. Fifthly, calculate the total load by summing all the base, heating, cooling, and miscellaneous loads. Sixthly, determine the service size. Multiply the total load by 125% as a diversity factor, and then round up to the nearest standard service size, such as 100 amps, 150 amps, or 200 amps. Moving on to motor load calculations under the 1987 National Electrical Code. Firstly, gather motor information. This requires obtaining motor nameplate data, including horsepower, full load current, and power factor. Also, note the starting current, which is typically 6 times the full load current for motors equal to or less than 1 horsepower, and 5.5 times the full load current for motors greater than 1 horsepower. Secondly, calculate the motor load. Determine the total current by multiplying the full load current by the power factor. Also, note the starting current, which, as mentioned before, is either 6 or 5.5 times the full load current. Thirdly, determine the conduit size. For the total current, use National Electrical Code Table 310.16 for conduit size selection based on the current rating. For starting currents greater than 100 amps, direct the conduit size by 1/3. Fourthly, address overcurrent protection. For overload protection, set the overload device to trip at 115% of the full load current. For short circuit protection, use a fuse or circuit breaker rated for the starting current. In calculating single-family dwelling loads, the initial step involves accurately determining the dwelling's electrical characteristics. This includes obtaining the precise square footage, which directly influences the lighting load calculation. Furthermore, it is essential to note the number of occupants, as this could affect the overall demand for electrical services. Accurately identifying the occupancy type, classifying the building as a residence, is crucial for applying the correct set of standards from the National Electrical Code. The next phase involves calculating the base load, forming the foundation of the overall electrical demand. This encompasses the lighting load, traditionally estimated at 3 watts per square foot. This value accounts for general illumination needs throughout the dwelling. Additionally, a standard allowance of 1500 watts is made for small appliance loads, covering typical household conveniences. Calculating the heating and cooling loads represents a significant part of the total electrical demand, especially in regions with extreme climates. For dwellings utilizing electric resistance heating, an estimate of 10 watts per square foot is commonly used. When dealing with cooling loads, a factor of 3.3 watts per square foot provides a reasonable estimate. The variability in climate conditions and insulation efficiency may require adjustments to these figures. Miscellaneous loads encompass a variety of appliances and equipment contributing to the overall electrical demand. Water heaters often draw around 1200 watts, representing a constant load for maintaining hot water supply. Electric ranges, essential for cooking, can draw 8 kilowatts, while electric dryers are estimated at 5.5 kilowatts. Electric ovens and other cooking appliances contribute about 2.4 kilowatts to the load. Air conditioning loads, critical for maintaining comfortable indoor temperatures, are calculated at 1.25 kilowatts per ton of cooling. Additional miscellaneous loads, including dishwashers, garbage disposals, and ceiling fans, should be estimated based on the specific appliance ratings and anticipated usage patterns. Calculating the total load involves summing up all the individual load components to arrive at a comprehensive figure. The total load represents the overall electrical demand for the dwelling, providing a basis for sizing the electrical service. This figure includes the base load, heating and cooling loads, and all miscellaneous loads. Determining the service size involves applying a diversity factor to the total load, accounting for the likelihood that not all electrical devices will operate simultaneously at their maximum rating. A diversity factor of 125% is commonly applied to the total load. After applying the diversity factor, the resulting value is rounded up to the nearest standard service size, such as 100 amps, 150 amps, or 200 amps. This ensures that the service can adequately handle the anticipated electrical demand. In motor load calculations, gathering motor information is the initial step, requiring careful attention to detail. Motor nameplate data provides essential parameters, including horsepower, full load current, and power factor. Horsepower indicates the motor's mechanical power output, while full load current represents the current drawn when the motor operates at its rated load. Power factor, a dimensionless number between 0 and 1, reflects the efficiency of electrical power utilization. The starting current, which can be significantly higher than the full load current, is crucial for sizing overcurrent protection devices. For motors rated at 1 horsepower or less, the starting current is typically 6 times the full load current. For motors greater than 1 horsepower, the starting current is 5.5 times the full load current. Calculating the motor load involves determining both the total current and the starting current. The total current is obtained by multiplying the full load current by the power factor. The starting current, as mentioned earlier, is either 6 or 5.5 times the full load current, depending on the motor's horsepower rating. Determining the conduit size involves selecting the appropriate conduit to accommodate the motor's conductors. National Electrical Code Table 310.16 provides guidance on conduit size selection based on the current rating of the conductors. When the starting current exceeds 100 amps, the conduit size should be derated by 1/3 to account for the increased thermal stress on the conductors. Overcurrent protection is essential for safeguarding motors against overload and short-circuit conditions. Overload protection is provided by an overload device, such as a thermal overload relay, which is set to trip at 115% of the full load current. Short-circuit protection is provided by a fuse or circuit breaker rated to handle the motor's starting current. The proper selection and coordination of overcurrent protection devices are critical for ensuring motor reliability and safety. The application of these calculations, rooted in the 1987 National Electrical Code, serves as a foundational methodology. By accurately assessing the electrical demands of a single-family dwelling and properly sizing the electrical service and protection components, engineers, electricians, and designers contribute to ensuring electrical safety, efficiency, and reliability for the occupants. These calculations, when diligently performed, mitigate the risks of overloading, overheating, and electrical failures, promoting a safer and more sustainable electrical infrastructure. In summary, the procedures for calculating single-family dwelling loads and motor loads under the 1987 National Electrical Code involve a systematic approach. This begins with gathering the necessary information, performing the calculations as outlined, and applying appropriate safety factors. The outcome is a safe and efficient electrical system that meets the demands of the occupants and equipment while adhering to established electrical codes and standards.